So in this video, we're introducing a brand new vector math operation. It's called the cross product. And so when you see an x between two vectors, that's what you call the cross product. So the cross product is an operation that crosses two vectors, and the result is a new vector that is perpendicular to both of the vectors that were in the cross product. So if you have an example here, if I take two vectors A and B and I cross them, the result is vector C, and you'll notice there that vector C is perpendicular to both A and B. A and B don't have to be perpendicular to each other, but C must be perpendicular to both of them. So this cross product, this vector math operation, is completely different than the dot product. Please don't confuse these two operations. I know that they look like multiplication, but in vector math, there is no such thing as just multiplication. There are vector operations, and one of them is the dot product, one of them is the cross product. And it's easy to confuse them with scalar multiplication when you have a cross or a dot. In regular scalar math, those things mean the same thing. In vector math, those two symbols do not mean the same thing. So that's why you must write every vector operation that you're trying to do. If you're adding two vectors, you got to write a plus. If you're subtracting two vectors, you got to write a minus. If you're dotting two vectors, you must write the dot. And if you are crossing two vectors, you must draw the cross. The interpretation for what this thing means is actually kind of interesting. The result of a cross product is actually an area vector. So it's a vector whose magnitude corresponds to the area spanned between the two vectors that are in the cross product. So a picture is a really good way to help you understand what this means. Let's say we're crossing vectors A and B. So A cross B is equal to vector C. That means that the magnitude of vector C is equal to the value of the area between vector A and B. So this kind of neon green area, that's the area that is spanned between vectors A and B. And vector C, the length of that arrow corresponds to the area between vectors A and B. And the direction of vector C must be perpendicular to both A and B. So to give you another idea of what this phrase spanning means, is that if you need to visualize the area that's spanned between two vectors, you just want to follow these steps. You draw your two vectors tail to tail, and then you kind of make like a parallelogram shape that kind of connects the vectors. So you draw two parallel lines, and then you can kind of visualize that area. And so I created a parallel line to B and a parallel line to A. And I draw those parallel lines at the tips of A and B. And so that area that's kind of encompassed between those parallel lines, that shape there, that is the area that is spanned between vectors A and B. Here's another example. Let's say we have vectors C and D. Again, I draw these parallel lines. I create this like parallelogram shape. The area between them is that shape that you can kind of shade in there if you needed to. That's the area span between two vectors. And so if you're crossing vectors A and B, the magnitude of that cross product is exactly equal to the area spanned by those two vectors. Another way to write that, instead of trying to figure out the area of a parallelogram, what you can do is use this equation right here. So the norm of the result of a cross product, let's say we're crossing vector A and B, the norm of that result is equal to the norm of A times the norm of B times the sine of the angle between them when they are drawn tail to tail. That is really, really important here. When you're doing dot products, we still said that the vectors had to be drawn tail to tail, but the cosine is actually more forgiving there. If you did the cosine of certain numbers are equal to each other, but the sine of these numbers is not equal to each other. So you want to be really careful that when you're doing a cross product, if you're using this definition here, that you must draw the vectors tail to tail, and it must be the smallest angle between them. So it must be the smallest angle between the vectors when they're drawn tail to tail. That gives you the magnitude of the cross product. to determine the direction of the result of the cross product, you're going to do something called the right-hand rule, which you kind of had some experience with when we talked about the Cartesian coordinate system, but now it's going to be more generalized to any cross product relationship. So you just have to learn these assignments, that the first vector in the cross product, like in this case A, that would be your pointer finger. The second vector in the cross product, that's your middle finger. And your thumb is the result of the cross product. So you make that shape with your hand, where you make an L with your pointer and thumb, and then you let your middle finger out, kind of like point outwards from your palm. And so it looks something like this, where A and B are the middle pointer finger and middle finger, and then C, that's the result of a cross product, let's say, is your thumb. So if you just use those relationships here, the right-hand rule will tell you the direction of any vector in the cross product. So if you know two of them, you can get the direction of the third one. And if you put these two things together, then you can do a product. This is called the graphical method. So graphically is like looking at pictures of the vectors, knowing their magnitudes and the angle between them. That's how you can do the cross product this way. You can get that resultant cross product answer. It needs a norm and it needs a direction because it is a vector. So let's kind of test ourselves out. Here's some examples. Let's say that we are looking for the direction of one of these vectors within this cross product. So we know that A crossed with B is equal to C. So in this example, A is going to be your pointer finger, B is your middle finger, and C is your thumb. So there's your result, your assignments again, just to remind you. Let's do this first example. So A, that's your pointer finger. That symbol means into the board. So point your pointer finger into your computer screen. B is your middle finger. That should be going to the left. My thumb right now is pointing up. So I would say that the answer to example number 1 is up. All right, example number 2. This time we don't know how to point our pointer finger, but we know that our middle finger should be coming out of the board. And our thumb should be going up. So my middle finger is out. I can see the tip of my middle finger. My thumb is pointing up. My pointer finger is going to the right. Sorry, no, to the left. To the left. All right, here's one that's kind of a little bit off. It seems odd. Your middle finger and your pointer finger, you can make any angle you want between your pointer finger and your middle finger. Those do not have to be 90 degrees to each other, actually. So point your pointer finger kind of up and to the left, and then make your middle finger go perfectly to the left. Now your thumb is going to be perpendicular to both of those. You want to put your middle finger and your pointer finger like in the plane of your computer screen. Your thumb should be coming out of your computer screen right now. So don't think that you only can cross vectors that are perpendicular to each other. You can try to cross any vectors you want. And some of them you'll get an answer, and sometimes you'll get a 0 if you try to cross particular vectors, which we'll get into. So go back and redo those examples if you're not getting the exact same answers as me. Analyze your right-hand rule and make sure that you are assigning the vectors to the correct parts of your right hand. And make sure you're using your right hand. Let's do another example. Let's kind of put all of this together. So we have vector M and vector P. They live on the plane of the board. We know their norms. M is 25 newtons and P is 10 meters. And we can see them there with their orientations as seen below. We want to figure out vector T. T is the result of crossing M with P. So M crossed with P is equal to vector T. The first thing I'm going to do is find the norm of the result of the cross product using that equation that I gave you before, that the norm of the result of the cross product will be equal to the norm of the first vector, the norm of the second vector, times the sine of the smallest angle between them when they are drawn tail to tail. So you probably want to redraw M and P so that they are tail to tail. So you can identify that angle correctly. So this was 30 degrees right here. All right, so I'm going to plug in some numbers. The norm of M was 25 newtons, the norm of P was 10 meters, and I'm taking the sine of the smallest angle between them. That would be this angle here. That's that angle theta that I'm looking for. So that would be 180 minus 30 minus 40. Plug all of that stuff into your calculator, and you should get 235 Newton meters. Don't forget your units. You had newtons and you had meters. You multiplied them together. That gives you a Newton meter. So we got the magnitude of the result of the cross product, but we need to describe its direction. So give your fingers these assignments. We're crossing M with P, so that makes M your pointer finger. P is your middle finger. So this one's kind of hard to do. I need my pointer finger to be going down. Actually, this one's not too bad. Down and to the left. My middle finger is going down and to the right. My thumb is coming out of the board right now. So try to make your fingers look like that. My thumb is coming out of the board. So that means vector t has a magnitude of 235 Newton meters, and it is coming out of the board. That fully describes vector t, which is the result of crossing M with P. Let's do a second example. This time, it's almost all the exact same information. We still have vector M and we still have vector P. This time we're looking for a new vector called S, and S is the result of crossing P with M. So notice before we did M cross P, this time we're doing P crossed M. So we're going to go through these same steps. Let's find the norm of the result of the cross product. That means we're going to take the norm of M, norm of P, sine of the smallest angle between them. All of that is still the same information. I'm still getting 235 Newton meters. So the area spanned by those two vectors is the same whether you cross M with P or P with M. The area is the exact same thing because it's the same two vectors. The thing that's different though, let's be careful when we find the direction of the result of this cross product. This time it's P crossed M. So that means P is your pointer finger and M is your middle finger. This one is harder to do. So we need P to be going down and to the right, and you need M to be going down and to the left. This time, my thumb is pointing into the board. And so vector S points into the board. So it has a norm of 235 Newton meters, but it points into the board. So to kind of summarize that all together, we crossed M with P, that was vector T, and T had a norm of 235 Newton meters, but it pointed out of the board. S was crossing P with M, so the inverted order of the two things in the cross product. And notice that T and S have the exact same norm. That area spanned by the vectors is the same. But the direction of the result of this cross product depends on whether we were crossing P with M or M with P. The order of the vectors in the cross product operation does affect the direction of the result of the cross product. So vector T and vector S are exactly opposite of each other. So if I was going to kind of summarize the important properties of the cross product here, this very first one is what we just saw. It's called anti-commutativity. That means that A crossed with B is the exact opposite as B crossed with A. So the order of the vectors within the cross product is important. It will change your answer. It'll change the direction of your answer. They're exactly opposite to each other. Another one that will come up eventually is that it is distributive across like scalar addition or subtraction. So if I'm crossing vector A with all of this stuff in the parentheses, you would kind of FOIL it out, just like we did previously with the dot product, and you can kind of group the scalars at the front. And just be really careful with the order that you are crossing vector A with B, and then you're crossing vector A with C. And so that's why I wrote these two things in parentheses as A cross B and A cross C. Order is important there. And then the last property is actually, you may have seen it, you may have identified it before, is that if you cross two vectors that are parallel to each other, then you're going to get a cross product of 0 because the angle, the sine of the angle 0 is the number 0. So if you cross a vector with itself, then that means that the result of the cross product actually is the 0 vector. I'm sorry. So it's the 0 vector if you cross a vector with itself. There is no area between a vector with itself. So that's another way of thinking about that the magnitude of the result of the cross product is 0 in that case. And those are some important properties of the cross product, and you can get some more practice performing cross products using this graphical method.